Good morning, everyone. It's a pleasure to again welcome Gillian Foulger to present to us today. She's going to talk about a plate model for Iceland in the North Atlantic Igneous province. I think most of you will be aware of her background. We will circulate her CV as well. So over to you, Gillian.
Thank you very much, John, and it's a pleasure to address you all this second week. So in the last lecture, I gave a kind of general overview of why my colleagues and I doubt the plume model. And in this slot, I'm going to talk in detail about one province with which I'm extremely familiar, and that is Iceland. So I first went to Iceland in 1977, so I've been researching it for over 40 years. And this is one place where I can actually say a lot because I had the good fortune to work with people who were extremely cross-disciplinary. I was using the method of passive seismology. I was looking at earthquakes to do my particular work, but we were expected to sit with all the people with geology and gravity and petrology and geochemistry and this, that, and the other, and come up with a holistic answer, because at the end of the day, I was working in geothermal energy. So when these guys drilled a well, they expected to find hot water and steam at the temperatures and pressures predicted. So we were in a position to kind of ground truth what we were predicting. You know, we didn't have the luxury of doing deep mantle probing or something like this, where you come up with an answer and nobody can check whether you're right, because it's not possible to drill down to 600 kilometers depth. You know, we were working in a field where you made these predictions and somebody tested to see if you were right. So I think that probably turned me into a different sort of scientist from the environment that many of my colleagues work in. Anyway, enough of the waffling. So let me, if I move to the next slide. So here we have Iceland, Northeast Atlantic Ocean, and this is a bathymetric map. Iceland, as colleagues will probably know, is this large island in the middle of the ocean. And here we have Britain, and here we have Greenland. And so we've got the deep sea floor here in blue, and the continental shelves are in pink here. And this, excuse me, this bathymetric illustration nicely shows up that excuse me, the region from the Faroe Islands, which is this little archipelago here, through Iceland to Greenland is all pretty shallow. So it's not like the ocean floor to the south and the north. There's a shallow ridge across here, and this is known as the Greenland-Iceland-Faroes Ridge. Iceland itself is volcanically active, obviously, with widespread volcanism, and in the 40 years that I've studied it, I've become familiar with all the details and all the problems and all the things that we don't understand. So I'll share that with you today. This slide shows the conventional picture. So if you look on the web or you look at some paper, then this is generally the simplistic way in which it's presented, with the Reykjanes Ridge spreading ridge to the south here, a transform zone across South Iceland, a spreading zone right across Iceland from south to north, a fracture zone here, the Kolbeinsey fracture zone north of Iceland, and then the Kolbeinsey Ridge and the Mons Ridge to the north. This is a very simplistic plate tectonic kind of model, and it's what we teach our students, and it's what I assumed was correct to begin with. But the more you come to know about Iceland, and I suspect, you know, when I say Iceland, think of your own province, the more you learn about it, the more you find it's not so simple. This diagram shows some of the complexities here. When the North Atlantic opened at about 54 million years ago, the new spreading ridge, the Mons Ridge, what's now the Mons Ridge and the Kolbeinsey Ridge, they run down the old Caledonian suture. So here we have the Caledonian frontal thrust in Greenland, the western frontal thrust, and here we have the Caledonian front in Norway. And these, of course, were once quite close together, separated by a couple of 100 kilometers. And then the continent of Eurasia split again down the middle, and these two were moved apart. South of Iceland, however, the situation is different. The Caledonian orogeny ends at roughly the position of Iceland here. And south of Iceland, the North American craton was split. So these relationships are seen not only in the mapped orogenic fronts in Greenland, but also in Britain. So we know that this is the case. We have a microcontinent here. We know that there's continental crust in the ocean here. And we have a double spreading ridge to the north, the Io Ridge here, and the Kolbeinsey Ridge here, this one being extinct. So the picture is much more complicated as soon as you look at the details. Moving quickly on to Iceland itself, this is what the neovolcanic zones look like. This is the region to the south, which in the simplistic model, you may recall that it's assumed just to be a transform fault. But as soon as you look at a map like this, you can see that it's not a transform fault. In pink are marked lavas younger than 10,000 years, and these are strewn right across this zone here. We have a mass of on echelon spreading zones. So each of these is a spreading zone. So in the northeast here, we have this volcanic zone here with 5 or 6 on echelon spreading zones. They are run parallel to each other south of this ice cap. And here we have another one in central Iceland, another one in western Iceland, and another one on the Snæfellsjökull Peninsula. This mountain here is Snæfellsjökull. It's a beautiful pinnacle type mountain, and it's the mountain that Jules Verne's heroes went down to reach the center of the earth. So that's a quite interesting fact. The spreading plate boundary out at sea, of course, the neovolcanic zone there, the zone where there's diking and fissure eruptions and so forth, is often quite shallow, quite narrow, just a few tens of kilometers perhaps wide. But in Iceland, the zone of active volcanism is 400 kilometers wide, and there are many parallel zones spreading at once. It also has propagating and dying ridge pairs. So this volcanic zone here is propagating south, and the southernmost tip is down here in the Westman Islands offshore. Goodness knows what's going on here. Nobody really knows. People just look away when you talk about this volcanic zone here, but there have been recent eruptions here. If we look at the earthquakes, instead of seeing, as we do along the mid-ocean ridge, just a narrow zone of recent earthquakes, there are earthquakes all over the place. And in fact, their locations do reflect the active zones. So here we have earthquakes here. These bunches are associated with highly active central volcanoes. And up here, as you can see, just a simple glance at this so-called fracture zone immediately reveals that it's not a simple transform zone, as we see on the sea floor. This is the southernmost transform zone, just to give you a little bit more detail, just to drill down a little bit more into the detail. So if this was a simple transform zone, there would be a clear morphological feature, like the San Andreas Fault, for example, going from west to east. And we would expect the southern plate to be moving to the east and the northern plate to be moving to the west. So seismology over the past century or so has shown that instead of there being an east-west fault, which moves in a shear east-west left lateral sense, we have an array of north-south faults, all of which are moving in a right lateral sense. So this completely opposite pattern of motion and faults, in fact, releases stress in the same sense as the one that you might expect. And what's going on in this zone here is that we have north-south trending faulting blocks, and we have bookshelf type faulting as indicated in this little cartoon top right. We also know that this seismic zone was further to the north, just we see these young post-glacial lavas offset. So just over periods of thousands of years, this entire zone is gradually migrating south. In addition to that, this is kind of backing out a little bit. Here you can see the this southern propagating tip that I alluded to earlier, and you can see a nice curvature to the active volcanoes here. So this is looking very much like a propagating, curving ridge tip. But what I've drawn here is all the currently active and extinct spreading zones that we know in this Greenland, Iceland, Faroes swathe. So in purple are currently active ones. There's a mistake here. This should be an extinct one. I need to correct that. So this zone here was active just a few thousand years ago. This is the currently active zone here. So these are producing volcanoes just on a decadal basis. This is active. This is active too. There is an extinct spreading ridge here, one here, one here, one here, one here. And also to the east, extinct ridge, extinct ridge, extinct ridge, extinct ridge. There we go again, pressing the mouse button, extinct ridge here. So the situation in Iceland now, where we have crustal extension going on over a zone hundreds of kilometers wide on multiple spreading zones, this has been the norm for the entire 54 million years of opening of the Northeast Atlantic. This isn't something that's just happening now. You know, this tremendous contrast with the very simple Reykjanes Ridge and the Kolbeinsey Ridge, both of which have been extensively studied in marine experiments. This very simple picture here just goes completely to hell in Iceland, and we have a very, very broad zone of extension on multiple fronts, and this has always been the case for the entire opening period. So the simplistic model is clearly, from what I've said, is just completely way off. It does not in any way predict or describe the observations that we see on the surface in Iceland. And I haven't even begun to talk about the crustal geophysics. I'll be talking about that later in the talk. So my colleagues and I, we formed a big think tank and held a series of meetings in Durham a while back. Jim was a stalwart central person in that think tank, and he flew over from Hawaii 4 times to Durham to participate in this thrust. I posted so many new research items on our website mantelplumes.org that I just had the kind of sense that we'd got enough on the table here that we could come up with some sort of model which would explain all of these strange, unusual, seemingly unique features in Iceland. I mean, I knew that the plume model could not explain this. You can always say, well, there's a plume here and the plume did X, Y, and Z, whatever you happen to see, but that's an a posteriori prediction, isn't it? That's changing the theory to match what you see. And every time you do a new experiment, you change the theory a bit more. So I didn't think that was satisfactory, and I felt that something else was going on. So we got ourselves together to take a look at this. And putting together all our knowledge and expertise, this is what we came up with. So this was the situation at about 54 million years when the continent of Eurasia became heavily disrupted in this region here, and rifting and volcanism started as a prelude to new ocean forming. The red here are seaward dipping reflectors, which we think are flood basalts, and the pink is flood basalts, which are also mapped offshore. So this whole region here lit up. It's interesting to note, you know, we tend to think of the distance from between the region between Norway and Britain and Greenland as being ocean. But looking at this diagram, there's a tremendous lot of region. There's a very big width of material, which is continental, which is now founded in the ocean, regardless of anything more that I'm going to say.
Yes.
I can hear somebody has not muted themselves.
If someone's talking on a cell phone, please mute.
This diagram shows some work by Dieter Franke, where his institute in Germany, the BGS, did a series of marine experiments in the South Atlantic. And they showed convincingly that the South Atlantic opened in steps, and that there was a fast propagator which went from south to north, stalled at some continental feature. There was a hiatus, and then there was a further surge of opening along the next segment. So it really went pop, 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 segment by segment, south to north, and South America separated from Africa by basically a propagating crack. Africa and South America didn't all suddenly start drifting apart at once. We tend to see these on television programs and in textbooks, and people imagine that the continent broke up with a great crack and the two sides moved together. But in fact, a crack propagated along, and the two halves of the continent basically tore apart, just as you would tear a piece of paper. This also happened in the Northeast Atlantic, but it was a little bit different there. So a ridge propagated from south to north, from what's now the southern tip of Greenland north to approximately the latitude of Iceland. But at the same time, or a little bit earlier, in fact, a ridge propagated from north to south. So instead of having a unidirectional propagation, which separated the two halves, we had more of a complicated situation where a propagating crack opened up north of Iceland, and then one came propagating up from the south, and the two did not join up. If you have two cracks propagating in a brittle medium like this in opposition, then they do not join up at their tips. They overlap and they kind of propagate past one another, and one dominates and the other falls back, and you get this kind of what one of our group called dueling propagators situation, where each propagator is trying to overcome the other, if you like, but they never actually join up. A bit like modern politics, isn't it? So Iceland formed in the middle here. The situation is even more complicated than that. So this is Greenland, and this is Norway, and this shows the northern crack, the Eyre Ridge, which propagated down here. It opened in a kind of fan-shaped fashion. The excess opening at this latitude was balanced in the south by distributed continental extension in this western part of Greenland, and eventually this ridge became extinct, and full seafloor spreading was transferred over to the west here, breaking off a chunk of Greenland, which was then rafted like a little microplate into the ocean. This seems to me to be strikingly similar to the situation in the West Somali and Mozambique basins. So I'm sure there are colleagues in the audience here who know more about this region than I do. but something similar has been postulated to occur there. I'd be interested to hear if anyone has anything to contribute that after my talk. We looked at the magnetic lineation map because you know, there's been great improvements made to this map. This is a slightly old version I'm showing you here. But we decided to go back to basics and to look at the linear magnetic lineations and see if we could unravel more details of the spreading history of this region. So the first thing to note is that we have beautifully regular lineations south of Iceland and north of Iceland. And over on the continental shelves, of course, the pattern is very much different. So this is continental regions. These regions here, Rockall Bank and so forth, you can convince yourself that you maybe see some lineations, but it's very disrupted. And these regions are heavily magmatized continental crust. And it's the same over here on the coast of Greenland. But intriguingly, it's somewhat similar on the Greenland-Iceland submarine ridge here and the Iceland-Faroes submarine ridge here. So what we did was to just draw in the lineations which were completely, you know, beyond question, and to palimpsestically restore the region, if you like, to see what we got. And we came up with these 6 time slices. So this bottom right one's 52 million years ago. And this is just at the very beginning when the ocean started to form. So we have spreading on the Reykjanes Ridge, a couple of clear lineations. We have spreading on the Eyja Ridge here. And here in the Greenland, Iceland, Faroes zone here, the Faroe Islands are here, so it hasn't really formed yet. I've just drawn in the location of the rifts that we know existed at the time. So we took this through 40 million years, 30 million years, 25, 10, and so forth. And we came up with this picture of the situation today, which I'll blow up in the next slide so we can see it more clearly. So these are the lineations. We have relatively, not entirely, but relatively simple seafloor spreading going on to the south. In the north, it's kind of complicated, but not that complicated. We had the Eyja Rift rolling first, opening up in a fan-shaped way, balanced by continental extension in this green block here. So this green block here originally was whacked onto the east coast of Greenland here. So at the time, you would have just seen multiple parallel volcanic zones in the continent. But eventually this situation could not be sustained and all this became extinct and regular seafloor spreading started up on the Kolbeinsey Ridge here. And there we have nice clear lineations that nobody would argue with. But in this region here, we don't have any clear lineations that anybody could argue with. Okay, we've got lineations that people would argue with, but we tried to keep it as simple as possible here. So what we have here, which I kind of showed in an earlier slide also, is an array of on echelon currently active neovolcanic zones here in red, and these blue ones are old ridges now extinct. They became extinct and spreading jumped inwards. So to begin with, the westernmost and the easternmost ones would have been active. After some period, these became extinct and spreading jumped to this one and this one. These became extinct, spreading jumped to this one and this one. And now these have become extinct and spreading is here. So you'll be building up a picture of multiple, 2 perhaps, maybe 3, we don't know, we don't have that degree of resolution, but say at least 2 ridges active at any one time. And as the ocean widened and these maybe were separated, they became extinct and jumped inwards. So I'm now going to talk about some of the things that some additional things that need to be explained. And one is this very, very curious thing, the so-called Thulian root. It's known from paleontological information, plants with discoid dispersal modes. Those are plants which just drop their seeds close to themselves, so they can't, the seeds are not blown long distances. If you see a plant, say in the Faroe Islands, and you also see fossils in Greenland, then these are plants where the seeds were not blown a long distance across the ocean. They had to have spread on land because they just drop their seeds close to the plants themselves. We also have information on the time of overflow of ocean water from the northern oceans into the south. And we know from this information that this zone here was subaerial until about 10 million years ago. So for the first 40 million years of ocean opening, there was a land bridge here. And colleagues who are familiar with the saga of Alfred Wegener and the attacks on his continental drift model will find this quite curious, because one line of attack, when Wegener pointed out that fossils were similar on both sides of the South Atlantic and in Brazil and also Southern Africa, colleagues suggested that these animals had trotted across land bridges which were now subsided under the ocean. And other colleagues, Wegener's supporters, thought this was ridiculous and absurd because there was no evidence for such bridges. And this is the one place where there was such a land bridge, it appears, at least one that spanned the entire ocean. So this must have been a very curious place indeed. This ridge now stands much shallower than the ocean basins to the south and the north, as you can clearly see from this bathymetric map. And this has been modeled thermally. It's been modeled assuming that the whole of this was oceanic and that it cooled and subsiding. And an oceanic composition is found to conflict with estimates for plate cooling. It should be much deeper if it were oceanic. So moving on to the model that the group developed. Colleagues will be pleased to see this, a smattering of continental geology. There's just to show a few more details. So here we have the Caledonian Front in East Greenland. Here we have the Proterozoic Naxoquidian origin, and there's another origin down here. So unfortunately, before you get too excited about all of this continental geology, I'll point out to you that all of this is ice cap. So very frustratingly, we can't see what's under that much. So what we think is that to begin with, when Greenland and Europe were juxtaposed and a new spreading ridge started to develop, it ran down the Caledonian orogeny. And when it reached the orogenic front, that's the region where Iceland now sits. So it would have run across a feature something like this. So this is a cross-section across the Himalaya Tibet orogeny, and this is what colleagues imagine is the structure underneath. So colleagues see a huge mountain range here, heavily eroded, of course, and underneath a mass of the very latest part of subducting slabs, which form a greatly thickened region of lower crust here underneath the orogeny. So the line of breakup would have run down the orogeny, and when it crossed the orogenic front, it would have gone across something like this. So we think that something like this, some sort of structure like this, with the very last subducting pieces of slab would lie across the region here. So most to the north of Iceland, the line of opening would have run along the orogeny. So it might have run along here, for example, way out back into the paper. But when it reached the Iceland region, it would have tried to cut across this. So we think that it was unable to do this we think that the northernmost propagating ridge propagated down to about this point here, the southernmost one propagated up here, but the region in between could not be so easily broken because the line of breakup was trying to propagate across the grain, the structural grain, if you like. So instead, there was extended period of continental stretching here, and this orogenic front shown here ended up being stretched like this here. And in fact, we think that it still is stretched, and that under this zone here is a large amount of continental crust. We modeled this numerically using a model like this, where this is the surface down to about 900 kilometers depth. So this orange zone here is the crust. This is the mantle lithosphere. This is the upper mantle, oops, and the pink is the lower mantle. And this purple block here, this represents a thick slab of probably largely eclogitic material, which is the mass of the very latest slabs, the very last slabs that were subducted, which just got plated onto the base of the crust and didn't drop off into the mantle. So we then stretched this. So Greenland's over here, Faroe Islands are over here. So we stretched this and saw what happened dynamically. So I'll run a animation now, and what you'll see is that as we run it for approximately 60 million years, which represents the opening period, this drops off. So this negatively buoyant eclogite drops off in two huge blocks. It sinks down through the upper mantle. There is, of course, return flow of warm material, which goes straight up to the base of the lower crust. It warms it up to some extent and enables it to flow in a ductile fashion for the full opening period of the at least up to the present day. We have actually run it in the future, and if this model is correct, which it doubtless is not, but you know, it's as close as we've come to a model so far, we might expect to get full seafloor spreading in the Iceland region in maybe 10 or 20 million years, and then Iceland itself will gradually subside beneath the ocean, and the poor Icelandic people will have to move somewhere else. So here's the stretching going on. Two huge blocks of eclogite drop down to the base of the upper mantle, dragging the mantle lithosphere with it, and asthenospheric material has risen up, becomes adjacent to the lower crust, warms it up, and enables it to stretch for the entire period. So I'll just run this again for you. These orange areas are areas where melt is produced, and it's very interesting. This model, we didn't sort of diddle it up to fit the observations. One of the colleagues who was involved in our think tank was already working on this, and he'd run many models. And when we came up with this idea, he said, "Hey, I ran a model, you know, which fit the parameters that you're talking about," and he pulled off something that he'd already got on the shelf to show to us. And this is what it was. So if you can see, there are always two zones of melt production. So this is actually also serendipitously predicting a double zone of spreading on the surface. So this is the situation at approximately 50.5 million years. And as I say, if we continued on and ran it, this crustal section here, it would continue to spread, and it would break at about 70 million years, and then seafloor spreading would onset. And if the ocean continued to open gradually, Iceland would suffer the same fate as the oceanic submarine parts of the ridge on either side of it. It would gradually subside beneath the ocean like the older Hawaiian Islands. So this is what we think the structure beneath Iceland is today. Here we have Greenland. We've got intact upper crust, lower crust, mantle lithosphere, and the Faroe Islands over here, which are known also to be continental, although capped with lava. And what we think we have in the in the offshore region here is stretched continental crust overlain by lavas. So in Iceland, colleagues who have been to Iceland will know that it's essentially 100% volcanic rocks. There's absolutely no evidence for any in situ continental crust on the surface. It's all covered with young lavas. But we think there is continental crust at depth, which is blanketed by lavas, just like the Columbia River basalts or the Karoo basalts, a huge region of flood basalt, which has got continental material underneath. So we studied the cross section there, and one thing that we haven't yet done is to study the mode of extension on the surface. So we've just done kind of a little bit of compare and contrast with some other regions for this. And this is a diagram of some overlapping propagating ridges from the East Pacific Rise. And colleagues have kind of mapped this through in time. So again, this is the present day here. And if you go back in time, closing it up, then you see this gradual development of the structures here. So this is not unlike what we see in the Iceland region, where there were obviously old axes of spreading here, which are no longer volcanically active. And the volcanically active region is in the middle here. And as crustal widening has proceeded, these parts of the ridge have become too separated to be sustained by the magma source. And so they've become extinct. They've been sloughed off into the separating plates, and there's been a lateral migration of the rift. So this model, probably a lot of our colleagues who also work on Iceland have consigned us all to the loony bin. But in fact, we may not have conveyed our message efficiently enough, because I'm very optimistic that this solves a tremendous lot of problems which were either unsolved previously, unexplained, or only by really stretching the parameters to the maximum that you possibly could be in any way accounted for. So I'll quickly run through a few of these. So the first one, most of these are geophysical. As I mentioned, I haven't actually spoken about the geophysical data yet, but I'm going to now. So there's something called the thin crust versus thick crust controversy in Iceland. In the 70s and the 80s, a lot of seismic surveying was done, and colleagues who did that came to the conclusion that the Icelandic crust was quite thin. It was only 7 to 11 kilometers thick. And underneath was a region which had a P-wave velocity of about 7.2, and that this was mantle. It had a somewhat low velocity, and this was because it was hot and partially molten because there was a plume underneath. So this model of a thin crust underlain by a hot, shallow mantle was fully consistent with the plume hypothesis. In the 90s, some more sophisticated seismic experiments were done, and it was concluded that what earlier colleagues had seen was just the upper crust, and that this 7.2 material was in fact lower crust, and that the moho was at about 30 or 40 kilometers deep. So the crust was not 10-ish kilometers thick, it was 30 to 40 kilometers thick. It was cold, it was all basalt. This showed that the plume under Iceland had produced a tremendous lot of basalt because it was very hot, and that this thick, cold crust was fully consistent with the plume hypothesis. So you'll start to see why, I try to find better solutions. Very exasperating. The older crust beneath Iceland problem. So if you take Iceland itself and we close it up palinspastically, okay, so this is what Iceland looks like now. The oldest surface rocks in Iceland are approximately 15 million years old. There are outcrops of 15 million years here in East Iceland, and 15 million years, roughly speaking, in Western Iceland. So if we close this up, and go back in time to 15 million years, this is what we get. This ridge to the far east is here, and this ridge to the far west is over here. And obviously there's a block of some 100 kilometers, 50, 100, possibly more kilometers in the middle of Iceland, which is unaccounted for. So this must be older than 15 million years. So I'll just point that out again, not wishing to sound patronizing or anything like this, but if we close Iceland up, we throw away stuff in the middle for 15 million years, we know the spreading rate is 2 centimeters a year, roughly. We close it up, 15 million years, we get this here. So this material in the middle must be older than 15 million years. And in order to get this obvious required observation published, which I think if you took a 10-year-old child and a few pieces of paper on a table and you showed them this, they would understand it, and they would see that this has to be, this material in the middle has to be older than 15 million years. But it took me something like a year to persuade the editor that this wasn't bonkers, that this had to be the case. But sometimes the most obvious things are the most difficult to grasp. But anyway, so there's a block of older crust underneath Iceland, which we do not see at the surface. So there's immediately evidence here which requires material to lie at depth in Iceland for which there is no age dating or sampling evidence on the surface. This stuff is blanketed with younger lavas. This is a map of seismic crustal thickness under Iceland. There's a patch in the middle, which is about 40 kilometers thick. It's about 30 kilometers thick over here and about 20, 25 kilometers thick over here. Clearly, if there was a plume under here, then instead of having a patch of thick crust, you'd expect a band of thick crust, because this plume is supposed to be moving in this direction here. So it's possible that this is a block of continental crust. We just simply don't know. We just know that there's a patch of very thick crust under Iceland. We also know something about the composition of Icelandic lower crust. So I don't have time to go into the details of this, but simply put, if you compare the gravity fields to the elevation, you are required to come with the conclusion that the lower crust under Iceland, or the so-called lower crust, has got a very high density. Its density is approaching that of the mantle. This thick region, this 20 to 30 kilometers, which we now think is lower crust, which formerly was thought to be hot upper mantle, it's got a density which is very close to that of the mantle and much higher than oceanic lower crust should be. This can be explained if the composition of this lower crust, if there's a great deal of continental mid and lower crust in it, if it's not oceanic. And also it can explain the problem of the magma volume. So the problem is that Iceland is too cold. The lower crust under Iceland is subsolidus. Many petrological investigations have also been performed to try to get a handle on the temperature of the mantle underneath Iceland. And this is taken from a paper on which Jim is a co-author, and he can speak to this if colleagues want further information. But essentially, if you gather together all the temperature estimates for Iceland and Greenland, you come to the conclusion that there may be a temperature anomaly. It may not exist now, it may have existed in the past, but the temperature anomaly is in the kind of 50 degrees to 100 degrees ballpark. It's not really, there's no evidence that under Iceland there's an anomaly greater than that. And yet here we have 40 kilometers of crust. And with a temperature anomaly of, say, 100 degrees, it's not possible to produce 40-kilometer thick thickness of basalt compared with the 6 kilometers that we see on the sea floor at ridges at a temperature which, just is a little less. So it's completely out of the question. To produce 40 kilometers of basalt would need astronomical temperatures of the 1600, 1700, goodness knows what temperature range. So then there is the case of the Thulian land bridge, of course, which sits far too high. So all of these problems, plus the complications that we see in plan view, so to speak, with these migrating ridges, all of this is just immediately explained if there's the so-called lower crust underneath Iceland is magma-inflated continental lower crust. So these ideas need to be tested. We're in the process of moving ahead on these tests, but I won't be talking about that now because I'd like to wrap up now and move on to discussion. So thank you all for listening.
Thank you very, very much, Gillian. Somehow, hearing the word thick and thin crust just makes me hungry. But I'm sure there's a lot to talk about the controversy here. You can unmute yourself, put your hand up. Lou's name is up first. Lou, unmute yourself and speak to us.
Okay, thanks, Gillian. One very important thing that is totally relevant to your story is our discovery a few years ago of 3 billion-year-old zircons in a 6 million-year-old basalt or trachyte in the island of Mauritius, which implies that there must be a piece of continental crust below the island of Mauritius. And in fact, we have a similar story for Southeast Iceland, where we propose that there are also Precambrian zircons and Precambrian crust below one of the active volcanoes in Southeast Iceland. So we propose that this was a piece of the Jan Mayen microcontinent, and so our result for Iceland is totally consistent with what you've been saying to us today.
Thank you, Lou. Yes, I'm aware of both those pieces of work, and I'm excited to try to move this forward. And to that end, I have a young colleague in Iceland at the moment with his camper van and his girlfriend driving around the entirety of Iceland, planning to collect 50 to 100 samples in order to look for more of these old zircons. So I'd be very interested in any involvement from yourselves in that.
Okay, thank you.
Maybe you could update me with the inside track, Lou, because of course there's been a lot of arguing about those zircons. Some of them were found in sand. I'm aware of one that was found in situ in a dike. They're few and far between. People have criticized them on various grounds. For example, people have said that they've been brought in by tourists, and people have also claimed that they're due to contamination. So what's your position on the old zircons?
Well, in Mauritius, the reviewers of our papers tried to convince us that what we have is not real. These are, in fact, one suggestion was that little birdies ate some zircons in Madagascar and flew.
That's a new one.
I know, and flew all the way to Mauritius, which is 800 kilometers.
They would have had
to be, they would have had to fly against the prevailing winds. Another suggestion, and they would have had to remain constipated for an 800-kilometer journey. Another suggestion was that they were washed in from ocean currents.
Yes.
Once again, the ocean currents are going the wrong way. Tourists and zircons were trapped somewhere in the treads of 4x4 vehicles, and washed up in and were deposited somewhere in the beach sands of Mauritius. But we discounted all of these things because we managed to discover zircons in actual volcanic rocks in Mauritius, in trachyte rocks, and so they cannot have been birdies pooping into trachytes and stuff like that. So you know, and as far as the contamination story, yes, it is a big problem when you do this kind of work, because you have to be very clean in your crushing protocols and this kind of stuff. But we were able to argue that it could not have been a laboratory contamination, because the place where we did this crushing and sample processing was in Potsdam, Germany, at the GFZ, and no Precambrian rock has ever been processed in that laboratory. And so we argued, I think, made a very strong case that that these have to be real. We can constrain it a bit less in the Icelandic case. There's a lot of our argumentation relies on the geochemistry and isotopes of the basaltic volcano that we suggested overlies a piece of continental crust. And so the story isn't quite as robust for Iceland, but that's what I've got to tell you. I think we're going to be looking, we're going to be finding old zircons in a lot more places that they shouldn't be in the earth. So if I was a bit of a younger man, I would be able to go to Hawaii and test the hypothesis there. But I can have colleagues do that for me, for us.
Right. So it's very interesting to hear how you come up with a radical new idea, which not everyone's happy to hear, and it's just such an uphill battle to get the stuff published. You know, I have sympathy with colleagues who come up with a bunch of observations and just say, oh, the plume did X, Y, and Z, because you can just get your paper published straight off without any problem. But if you try to challenge a hypothesis, if you try to make a significant step forward, you're just opening yourself up to 12 months of battling, and multiple revision rounds.
Be persistent and stubborn, and one day the powers that be will see things your way.
Unfortunately for everybody around me, that's a very fundamental and strongly baked in aspect of my personality.
It's the successful Lou Ashwell model. Stephen Haggerty, how's Miami this morning? I mean, we need some input from you. Yeah, good to see you online.
Yeah, thank you.
Stephen? So we'll wait for him to wake up or get off his coffee. Other questions?
I'll come in, John, if I've got a moment.
Yeah, sure, Neil.
Gillian, enjoyed this very much, and I listened to a replay of last week and I enjoyed that a lot too, and I picked up what you said about the need for multidisciplinary skilling there. I think it's a really important message. One question, the Azores is much further south, I know, and my simplistic picture of that is it's rather simple. Or is it a case, if you look much more carefully as you've done of Iceland, that these simple models just don't work, of just simply pulling apart as we're told about, say, the Azores? Are there simple parts and difficult parts?
Well, the Azores, of course, lies on a triple junction. That's the first thing to note. I'm not aware of any zircons that have been found there, but I mean, the Azores, there's much less landmass exposed. This is one thing. Everything looks very simple if you don't have too many observations. The islands are quite small volcanoes, and it's a bit more limited what you can do. But certainly, if you compare the Azores up against the plume model that I described, there's a kind of that's a basic plume model. You see that there's very, very little about the Azores that fits the plume model. There appears to be no plume head, there's no plume trail, There's precious little, if any, evidence for any high temperatures. It's on a triple junction, so we're expected to believe that a mantle plume from the core mantle boundary smacked up just coincidentally on a triple junction on the spreading plate boundary there. It's in some ways it's like a little mini Iceland. If you look at the bathymetric and geoidal pattern, it's like that. But I think what we're looking at there is probably an unstable triple junction, which is volcanically active.
Well, thank you for that. That gives me quite a bit to go away and think much more about. But on the plume thing, if you, in your little animation, around about 50 to 60 million years, you had 3 pink things rising from great depth. Why wouldn't you descriptively call those mantle plumes?
The mantle plume model that we're objecting to is the so-called Morgonian mantle plume model, where plumes arise from the core mantle boundary and they're relatively fixed there. So they rise from the core mantle boundary at a fixed position and they rise up through the entire mantle. We're not saying that a diapir in the upper mantle is impossible. In fact, we think that there is extensive convection in the upper mantle and there'll be up moving branches as well as down moving branches. It's this fixed, deep, hot mantle plume model that we're up against.
That's clear. Thank you.
So effectively what you're saying, Gillian, there are mantle perturbations or, whatever you want to call them, hotspots or linear bands of heat, which play a role much like yours. And I'm glad Neil raised it, those color spots on your model.
What we're saying is that the Morgan model of the deep mantle plume fixed at the core mantle boundary, rising up through thermal buoyancy and punching through a passive lithosphere and remaining fixed and producing a time progressive trail, that model does not agree with the observations that we see at proposed sites. We're not saying that upwelling diapirs do not occur. However, we are saying that the lithosphere is the active element. We're saying that it's lithospheric extension that's permitting hot material to erupt. We're saying that, regardless of, okay, so if you could have some situation where you have a hot diapir in the upper mantle, this is a reactive feature. It's reacting to what the lithosphere has done. It's not an arbitrary thing that you can just put anywhere you like and it's going to punch up and go through the lithosphere and the lithosphere doesn't know what it's got coming sort of situation. If material is rising up in the upper mantle, it's a reaction to what the lithosphere is doing. We know that plate tectonics is fundamentally driven to a majority extent by downgoing slabs. It's the negative buoyancy of downgoing slabs that is causing extension in the plates, and this extension is causing the upwelling of the mantle. So that's quite a key conceptual thing. I read tremendous lots of papers saying, oh, we've got volcanism here, we've got rifting here, and blah blah blah, and the mantle must have been hot here and risen up and done this and then flowed laterally, as though the mantle itself is just kind of organizing its own heating and cooling and it's telling the lithosphere what to do. I don't think that's the case. I think the lithosphere, the dynamics of the lithosphere, fundamentally, plate tectonics, is causing the mantle to react. Just as in that animation that I showed, we stretched the lithosphere. It stretched, it destabilized, it lost its eclogite block, and the mantle welled up in reaction to that.
Okay, the chicken and egg or egg and chicken situation in some respects. Sue, I see you had your hand up.
Yes, Gillian, that model you just mentioned, does that actually require layered mantle convection? or are you allowing it to have whole mantle convection, or is that a boundary condition at the bottom of that mantle? That model?
There could have been whole mantle convection, it just didn't happen. You know, the lower mantle is obviously much more viscous than the upper mantle. And so it's much more difficult to make the lower mantle convect. The lower mantle is much more sluggish convection-wise than the upper mantle.
So you're arguing, I mean, you're saying this is evidence for layered mantle convection, certainly under Iceland.
I think the physical properties of the lower mantle are such that it convects on a much longer time scale. You know,
I'm trying to understand in your model how deep that disturbance goes. So in that particular model, is that at the transition zone, or does it go through the transition zone?
There was some disruption of the base of the transition zone, yes.
Okay, that's what I was looking for. Thanks.
But it didn't go right down to the core mantle boundary.
Yeah.
You know, once these delaminating slabs hit the base of the transition zone, it's like hitting a wall, really. You know, there's much more resistance to deeper disruption.
And that sort of, I mean, the blob structure and those sort of parallel processes that started, I mean, is that again just a simple delamination, or that the eclogite layer got too heavy and it had to sink?
Basically, yeah. So it's kind of clinging on there in a you know, potentially unstable situation, really. And as soon as the lithosphere was disrupted, it enabled it just to peel off.
And what other, I mean, I think you've obviously looked at it very carefully. I mean, what other rocks? I mean, is there any, you know, more alkalic basalt sequences at the start of the Icelandic eruptions, or is it all just layers and layers of tholeiitic basalt?
This is another interesting point that you've touched upon, and if James hasn't gone to sleep, I'll call upon him to speak to that, because he's done a lot of petrological work in Iceland, and I'm sure you want to hear a voice different from mine for a change. Basically, are you there, Jim? 10% of the rocks in Iceland are andesitic or acidic.
Am I muted or not? Muted?
Oh, you're there now. John is asking about the petrology of Iceland. I just mentioned that 10% of the rocks are andesitic and acidic.
The question had to do with alkalic, which might be basanitic, alkalic basalt, nephelinite, or something like that. And
correct. Yeah.
Most of the stuff, let's say in the Labrador Sea, is tholeiitic to, excuse me, picritic tholeiitic. Almost all of it is. And almost everything we have on the ocean floor is the same. There is about 7 or 8% of the spreading ridges produce a kind of transitional to alkalic kinds of composition, but no nephelinites right at the ridge axis, none. So you only get out to ocean islands to get to those kind of rocks, and you get very small volumes of them. I think there may be, excuse me, in parts of Greenland, some basanite, nephelinite kind of rocks, but I think they're very small volume, and I don't know exactly when they formed. So the big thing to explain, Al Engel used to say that the quantity of ink that's spilled over these kind of alkaline rocks is vastly out of proportion to the compared to the great volume of rocks that actually exist out there. The kinds of things you need to explain are the large volumes of tholeiitic, depleted kinds of compositions. Now, there's been a lot more done since then, since Engel was active. But the main thing we need to explain, I think, is why is there a huge volume of tholeiitic rock in Iceland, and what does it mean? There are places in, let's say, the Karoo Basin, where there are nephelonitic rocks, but they are fascinating rocks and hard to explain, and they contain neat things like xenoliths here and there. So you can get at a lot of different questions.
So Jim, when you say a huge volume of tholeiitic rocks in Iceland, what exactly do you mean? Because what I would expect is that there's approximately the same amount as there is in the ridges to the south and the north. It's just dumped on top of continental crust.
Well, yes, there are alkalic rocks in Iceland out on Snæfellsnes, and a few seamounts further west. There are no alkalic rocks, as far as we know, on Reykjanes or Kobeinsi ridges. Most of the stuff on Iceland is tholeiitic and tholeiitic differentiates, and there's about 20% of eastern Iceland is silicic. That's the stuff that has a potential likely source in some kind of continental, buried continental crust. You melt that stuff up and get it up to the surface. That's my personal opinion about it.
How do you explain the oxygen isotopes then, which suggest that they might be hydrothermally sourced?
Start my video. Somebody turned my video off. I didn't.
It was Henny.
All right. Let's see. Would you repeat your question? What it had to do with?
I said, how do you explain the oxygen isotopes, which seem to suggest that the silicic rocks result from hydrothermal activity?
Well, the silicic rocks do not result strictly from hydrothermal activity. First of all, they're way too large in volume, and they're way too directly connected to a differentiation sequence starting from tholeiites and going through a high iron differentiated with ferroandesites. It's a complicated thing to explain, but normal differentiation does not produce that quantity of stuff from tholeite. You have to have something else added to it. And whether that stuff had oxygen isotopes that were in the source that were different, maybe that's part of the explanation. Hydrothermal activity will not do it.
So before I forget, or before John gets rid of me, I just want to kind of recap that one research avenue we're trying to get going at the moment is to compare the geochemistry and the petrology of Icelandic rocks to those of continental flood basalts like the Karoo, which we know erupted over continental crust. So, here we are trying to explain Iceland in terms of having a continental substrate, but we don't have any samples. There's no outcrops of the stuff in Iceland. So the question is, how could this fit the geochemistry and the petrology? And the other unrelated thing is that I'm looking for one or two speakers for the Northeastern Geological Society lecture program. So everybody please volunteer.
Okay, we've got both those points, Gillian noted, and I think as Lou said last time, and Andy Duncan, was also on this call, and he put together most of the amazing Karoo geochemistry collection. There's no shortage of data from this side of the world. But just to add to that, we make this loose statement that all the Karoo sits, on the crust. Well, if you go look at the Lubombo, there was some pretty big breaks and dike swarms there and so on. Where you got the sense that was a sort of loci of probably the great focus of heat, and it begs the question. In the early, and that's where I was going with the nephelonites, are very, very small volume, but fascinating rocks. As the precursor to these big outpourings, and there probably was bigger breaks in the crust there. So we certainly see contamination, but some of the rocks there are also, relatively uncontaminated. And then, of course, we also have kimberlites, fascinatingly enough, that immediately precede the Karoo lava eruptions. Craig Smith, your comments, questions?
Thanks for the talk, Gillian. It was very good. Not much has been said about seismic tomography that I think has happened in the North Atlantic.
Yeah, I could talk about that in the next lecture, but I do have one slide. I thought this question might come up, so I cut it out so I didn't ramble on for too long, but I can show it to you.
If only you can find it.
I guess the question is relatively simple. Does the tomography show a deep plume trail or vestiges of a plume?
So can you see this slide?
Do we believe the tomography in the first place?
Can you see this slide?
Yes.
So here is our end model here. This is after 50 million years, and we've got this sort of counterflow here. And this is one seismic tomography picture anyway. So this structure here would be equivalent to this one here.
You'll have to walk us through it. It's a bit vague, Gillian, or blow it up next time.
Okay, so we've got this sort of pancake up here. I mean, basically this looks like a mantle plume, except it's the counterflow to the dropping off of these two things. So we've got this sort of top pancake here and this narrow feature underneath, and in the seismic tomography we've got a top pancake here and this narrow feature under here. So there's almost a one-to-one correspondence between this here and this here.
So the seismic tomography doesn't really prove or disprove anything here in this case.
I'll be talking about this in the next lecture, and one thing I'll show you is 4 separate seismic tomography images of the mantle underneath Iceland, and they're all completely different, because one message I'm going to send is that the repeatability between seismic tomography results is very, very poor. That the method is not very robust for showing us the detailed structure of the mantle below about 400 kilometers. So although, of course, people want to see plume stems or the lack of plume stems or whatever, I'm afraid seismic tomography will not just deliver the results you want just because you want them. Seismic tomography is reasonable under some circumstances for the upper few hundred kilometers. And some of my colleagues would even think that was being overly optimistic. But below that, it's just wild. Every single experiment essentially gives a different answer, unless you look at very big structures, which are 10,000 kilometers across. Then there's a certain amount of agreement. But on small scale things like plume stems, you can't see them with seismic tomography.
So are you saying you don't believe that strip that goes down to 1,200 kilometers beneath Iceland in the Rickards et al. Model?
I think there's a certain amount of repeatability of this thing. Yes, so there may be a weak anomaly going down deeper under Iceland, but it's clear that under Iceland there's a strong anomaly that occupies either the top few hundred kilometers, and there's a certain amount of evidence that there may be a weak tail which goes down to maybe the base of the upper mantle, 700-800 kilometers. But then there are models which don't see it, so it gets less and less reliable the deeper you go. and I'll be explaining that in detail in my next talk. So, basically, geochemistry, no geochemistry can tell us that stuff has come from the core mantle boundary, and seismic tomography cannot show us the detailed structure of the mantle below about 400 kilometers. So these two dominant methods, geochemistry and seismic tomography, which are used to research plumes, are not able to do it, basically. No geochemistry requires a core mantle boundary origin, and tomography can't see anything that's smaller than several thousand kilometers at those depths.
Okay, interesting.
Thank you. I think that sort of leads us into next week's lecture, the one thereafter. Then, and also the mere mention of pancakes and crusts tells us it's time for lunch, and people like James and the people in Australia to go to sleep. Thank you very much for a most entertaining discussion, and we hope to see you all here next week.
And Henny, just remind people it's a double presentation next week, the 14th and 15th. And what's it?
You get two for the price of one next week on
Correct.
Wednesday and Thursday at the same time of the day. So get some sleep in the afternoon, James, and our colleagues down there in Australia. We'll see you bright and breezy next Wednesday and Thursday. Thank you very much.
So, and Ben Hayes will be
See all of
talking.
you.
Yeah, absolutely. So Ben Hayes will be talking to us on the Wednesday, and Gillian will follow up on Thursday. So don't miss those two fascinating presentations.
I'm going to go watch the flowers in the Macquarie, so you'll be in the good hands of Dr. John Bristow next week.
Well, we're expecting you to dial in, Henny.
I'll log in if I can from amongst the flowers. Thank you very much for having you guys. Goodbye,
Okay,
everybody.
thanks, everyone.
And
Thanks,
all of these
Julian.
recordings, as
Thank
you
you.
know, are on our platform, the Odd 90 Odd One. So go and enjoy yourselves there too. Good day, good night.
Okay,
Thanks
take
very
care.
much from Cape Town.
Bye now.